Problem. A simple wood beam, 50 mm wide by 250 mm deep and 7.5 meters long, has a maximum deflection of 102 mm under uniform load W. If the third support is placed between the two supports to make the deflection equal to 0, given a modulus of elasticity equal to 12,411 megapascals, we are tasked to find the maximum bending stress in megapascals. And to solve this problem, you can use double integration, error moment, and any other methods, but the best approach to this problem, to make our calculations much easier, is by principles of superposition. And according to the method of superposition, the slope or deflection at any point on the beam is equal to the resultant of the slope or deflection at that point caused by each of the load acting separately. So let's say we have a uniformly distributed load that will induce a downward deflection. Let's call this deflection delta sub W, and it is going downward, so it's negative. We add this to the deflection induced by an upward force that is added at the midspan. Let's call this force P, and it would induce an upward deflection on the beam. Let's call this deflection delta P, and it's positive since it is going upward, all equal to a net deflection of 0 at the midspan of the beam. Now to solve this, let us first solve for the uniformly distributed load W by using beam formulas. For a deflection at midspan due to the uniformly distributed load, that is equal to 5 WL raised to the 4th power divided by 384 EI equal to the deflection at midspan, that is equal to 102 millimeters, which is given in the problem. Let's plug in the round values. We have 5 W times the length of 7.5 meters or 7,500 millimeters raised to the 4th power divided by 384 times the modulus of elasticity equal to 12,411 megapascals or Newton per millimeter squared. And for the inertia, for a given rectangular section, it is given by the formula BH cubed divided by 12, where B is the base and H is the height. So we have a base of 50 millimeters. Multiply this by the height, is equal to 250 millimeters cubed all over 12, and this is equal to 102 millimeters. Now we can solve for W. We have 5x, a length of 7,500 raised to the 4th power divided by 384 times EI equal to a deflection of 102. Shift solving, we get W equal to 2 Newton per millimeters. Now that we have the value for the uniform distributed load, we can proceed solving for the reaction P. We have a deflection due to the uniform distributed load that is equal to 102 millimeters plus the deflection due to the concentrated load at midspan that has a formula EL cubed divided by 48 EI equal to 0. Now we can solve for P by plugging in the known values. So we have negative 102 plus the unknown force P times the length of 7,500 millimeters cubed divided by 48 times the modulus of elasticity equal to 12,411 times the moment of inertia for this cross section that's given by the formula equal to VH cubed divided by 12. We have a base equal to 50 millimeters times a height of 250 millimeters raised to the 3rd power divided by 12 equal to 0. Shift solving, we get the reaction at midspan equal to 9,377.2 newtons. Now that we have the value for the reaction at the midspan, Let's proceed solving for the reaction at the other supports. By symmetry, these two reactions at the edges are equal. We can prove this by taking summation moment at the supports. So we can proceed solving by taking summation force vertical, considering upward forces to be positive. We have 2R going upwards and 9,377.2 newtons minus the uniform distributed load 2 newton per millimeter times its length to get the resultant. It is a length of 7,500 millimeters, all equal to 0. So we have 2R plus 9377.2 minus 2 times 7,500 equal to 0. Shift solving, we get the reaction equal to 2,811.4. This one is also equal to 2,811.4 newtons. Next, we construct our shear and moment diagram to locate the point of maximum bending. So let's begin with the shear. Going upward, it has a value of 2,811.4 due to the upward force. And then it has a uniform distributed load, so it will go downwards. It has a value of 2,811.4 minus 2 times half the span of the beam. This is equal to negative 4,688.6. Negative 4,688.6. And it goes up with a load of 9,377.2. It has a value of 4,688.6. Minus the uniform distributed load 2 times 3750. We get negative 2,811.4 plus the upward load of 2,811.4. This will become 0. Now that we have our shear diagram, we can proceed drawing our moment diagram. But first, we need to solve this distance, here x. And this distance here is equal to half the span, that is 3,750 minus x. Now we can do some ratio and proportioning with the triangles. We have x divided by the vertical distance, that's 2,811.4, equal to the horizontal distance of 3,750 minus x over 4,688.6. Shift solving, we get x equal to 1,405.7. Now to solve for the moment diagram, we add up these areas here to get the point of maximum moment, which is found at this point of zero shear. So we have base 1/2 base times height of the triangle. Which is equal to 1.98 times 10 raised to the power of 6. This is in Newton millimeters, and this here has a unit of newtons. Next, we subtract this by this area of this rectangle. You would get 1/2 base times height. This is equal to negative 3.52 times 10 raised to the power of 6 Newton millimeters. Then we add this up to this triangle here, but first we need to solve for this distance. We call it x, and this one is 3,750 minus x by doing some ratio and proportioning of the triangles. So the ratio of the horizontal distance and the vertical distance is equal to this horizontal distance of the triangle over its vertical distance. We get x equal to 1405.7. Then we add this up. 3.52 times 10 raised to the power of 6, and it's negative, plus this area of this triangle, which is 1/2, times the base of 3750 minus 1405.7 times the height of 4688.6, and you will get 1.98 times 10 raised to the power of 6. 1.98 times 10 raised to the power of 6 minus this triangle here, equal to 1/2 times base times height, which is approximately closer to 0. And the maximum moment is found at the midspan. There is a value of negative 3.52 times 10 raised to the power of 6 Newton millimeters. Now we can solve for the flexural stress. That is equal to moment times the distance from the initial axis to the outermost fiber divided by the moment of inertia. We get moment equal to 3.52 times 10 raised to the power of 6 Newton millimeters times the distance from the outermost fiber to the neutral axis, which is at the center of the rectangle. That is equal to 250 millimeters divided by 2, divided by the moment of inertia, which is given by the expression ph cubed divided by 12. We have a base of 50 millimeters times a height of 250 millimeters cubed divided by 12. We get our maximum bending stress. That is equal to 3.52 times 10 raised to the power of 6 multiplied by 250 over 2 divided by the inertia of 50 times 250 cubed divided by 12. We get our final answer, that is equal to 6.76 megapascals. And that is our final answer, which is closer to 6.75.